All right, Unit 9, Applications of Thermodynamics, our final unit for AP Chemistry. And we're refreshing what we talked about in Unit 6. So we're going to go a little bit more in depth. We're not going to just talk about enthalpy, but we're going to talk about something called entropy. And essentially, that's just a measure of the randomness in the system, or the dispersal of the matter. So how is that matter dispersed? It's a state function, so we're only worried about how the path, we're not worried about the path, we're just worried about the change. So final minus initial. Entropy increases in a phase change from solid liquid to gas. This should make sense because a gas molecule, like hydrogen gas, has way more dispersal than a liquid hydrogen molecule that's going to be much more tighter together. So they're more freer to move. That's going to have a higher entropy. There's more to it than that, but that's the outside the scope of our class. We're just going to stick with the idea that the more disorder or that the more dispersal is a higher entropy. Entropy increases with the gas, increases in volume, again, because there's more places where it can be, so that there's more disorder available. And then entropy increases with increasing temperature. That should also make sense because the energy increases. Absolute entropy and entropy change. Very similar to the way we were calculating enthalpy and H, but it's talking about entropy instead. We use S for entropy, and it's going to be still entropy is equal to, or the entropy of the reaction is equal to the entropy of our products minus the entropy of our reactants. Final minus initial. So what does that look like in practice? We have our reactants and our products. So it's products minus reactants. So our products are 192.5. And it's mole ratios, so we have to multiply that by 2, minus our reactants, which will be 130.6. There is no hydrogen does not have a coefficient, and then nitrogen is also no coefficient, so it's just 191.5. So we do 2 times 192 minus 130 plus 190, and you're going to get 62.9. So it's really important to pay attention to the signs. All of our signs are positive, and so we can end up with that value. Moles are important, so we always have to make sure with stoichiometry. And then we can also predict what's going to be happening with our entropy by looking at products compared to reactants. Now, in this case, we have two gases creating two gases, right? We have nitrogen, one gas, hydrogen, another gas, creating two gases. So that would be something where we wouldn't necessarily be able to predict the entropy change. But let's say one of those is a solid. It's solid reacting with a gas to form two gases. That means our entropy is increased because now we have more gas than we had previously. So when we increase the dispersal, we're going to increase entropy. Decrease dispersal, we're going to decrease entropy. To Gibbs free energy and thermodynamic favorability. So when we were talking about thermodynamics originally and enthalpy, we discussed how most of the time it's exothermic reactions were favorable, and endothermic reactions could occur, but why could they occur even though they require energy? And why could they occur spontaneously even when they required energy from the system or the surroundings? And that gets us into Gibbs free energy. Gibbs free energy compares our enthalpy, our temperature, and our entropy to discover whether a reaction is favorable. It's another state function. And it just tells us, will this reaction occur under the given circumstances? And so standard conditions would be delta G is equal to enthalpy minus temperature times entropy. And we could also find Gibbs free energy based upon standard free energies of different species within the reaction. And then really important to note is that just because a reaction is favorable does not mean it's going to react quickly. Rusting is a favorable reaction, but it is a very slow process, generally speaking, when it happens spontaneously. You're not going to be putting a nail out and it's going to rust in 5 minutes unless you're applying energy to that system. So just because it's favorable does not mean that the rate is going to be anywhere discernible at times. Okay, so when we look at Gibbs, we want to look at the value of Gibbs to determine favorability. If it is less than 0, the forward reaction is favorable. If it's 0, our reaction is at equilibrium, neither side is being favored. And if it's greater than 0, the reaction is not favorable in the forward direction, but the reverse reaction would be favorable. So hopefully that makes sense. So less than 0, favorable, greater than 0, not favorable, reverse will be. So when we look at this reaction, we can actually predict favorability, or when we look at reactions, we can actually predict favorability based upon values of enthalpy and entropy, based upon temperature as well. So if we have an exothermic reaction, so less than 0 enthalpy, and a high entropy reaction, so our entropy has increased, it's greater than 0, it's always going to be a favorable reaction. If our enthalpy is endothermic, so greater than 0, and our entropy is decreasing, so less than 0, then it doesn't matter what the temperature is going to be at, we're never going to have a favorable reaction. Okay? And this should make sense. That means that it's taking energy to react plus the entropy, which is decreasing, is also going to take energy. Thinking about your bedroom. To keep your bedroom clean, it requires you to expend energy to keep that neat and tidy, right? And if you don't work on the energy to keep your room neat and tidy, what eventually happens, dust is going to collect, you are going to have dirty clothes on your floor, your bed's not going to be made. All of those things to keep your room tidy have to be energy expended to keep that entropy low. Low. I was right the first time. Low. Entropy naturally increases in a system for the most part. Okay? So when could we have an endothermic reaction and be favorable? Well, it depends on the temperature and the entropy, right? So if we have an endothermic reaction, this is our third one, and we have increasing entropy, what we would need is a high temperature to tell us that, well, that should make sense because then energy can be going into the system to overcome that endothermic factor. If we have an exothermic reaction, but our entropy is decreasing, so we have becoming more and more ordered, that will be favored only at low temperatures. Okay, so that the exothermic overwhelms the entropy part of it. Let's look at a math and maybe hopefully that will help make sense about why that works out. It says predict the thermodynamic favorability for the formation of nitric oxide from nitrogen and oxygen at 298, given that the enthalpy is positive and entropy is positive. So 298, So 298 is would be considered a low temperature. That's room temperature. That's not a very high temperature. I would say it's kind of medium, right, to low. Enthalpy is positive. So enthalpy is positive. So we have a high enthalpy. That means it's endothermic. But our entropy is also positive. That means we're getting more disordered. And remember, delta H minus T delta, S, not delta, but yeah. Okay. That's the equation that we're looking at. If Gibbs has to be negative to be favorable. So if we have a positive value here and a positive value here, the higher the temp, the more likely it's going to be favorable. 298 is not a very high temperature. So because 298 is not a very high temperature, we're going to assume that Gibbs is most likely going to be positive. And so if Gibbs is positive, it is not favorable. So just based upon our general knowledge of positive entropy and positive enthalpy, we assume and low temperature, we assume our reaction isn't favorable. Well, let's test it. Let's look at actual enthalpy and entropies of our system. So our enthalpy, 180.7 kilojoules, minus our temperature, 298 Kelvin. Okay, so very important here. Notice it's joules per Kelvin. So we need to change joules per Kelvin until kilojoules per Kelvin, which would just be joules, right? 24.7 joules per Kelvin. And for whatever 1,000 joules, we get 1 kilojoule. So we just divide by 1,000. And it's going to be 0.024 kilojoules per K. And K is going to cancel out, right, because we multiplied it by each other. And we end up with 173.3 kilojoules for our Gibbs free energy. So it's positive. That means it is not favorable. Just like we predicted. All right, 9.4, thermodynamic and kinetic control. All right, kinetic control, all that means is the reaction can be thermodynamically favored but occur at a very slow rate. We just already talked about this, right? It's thermodynamics or favorability doesn't necessarily mean that it's going to happen at a place that we can see. Generally, that means that there's a high activation energy. So that's the kinetic control. So if a reaction has a really high activation energy, it's going to happen really slow even though it's favorable. So things like rusting or the decomposition of ammonia, all of these things happen at a really, really slow rate because they have higher activation energies even though they're favorable. Okay, free energy and equilibrium. So how does this tie in? So just the idea that at equilibrium, our Gibbs free is going to be 0, which then also we could talk about when delta G is near 0, equilibrium constants will be close to 1. So when delta G is much larger or smaller than our R over times T, which R comes from our gas law constants. the value is going to deviate from 1. So K is 1. We know we have no favorability one side or the other, and it's just very much at that equilibrium. The greater it is, the greater at 1 is, the more the forward reaction is favored. Smaller, the more the reverse reaction is favored. Remember that, going back to equilibrium. And it still applies to Gibbs. 9.6 coupled reactions. So when we have an unfavorable reaction, but it's something important in industry to have the reaction occur, they'll do something called a coupled reaction. Essentially what that means is that you have one reaction that is coupled to another. They react at the same time with a common common species. We can make that unfavorable reaction occur. It's used a lot in industry so that we can create a reaction that actually gets us our material at a decent time. Electrical energy like a battery, that is used it, so we can use batteries to create that reaction from happening. We're going to talk about batteries during this unit as well. And then also things like another naturally occurring one is light driving CO2 conversion to glucose in photosynthesis. Okay, so the individual reactions share one or more common intermediates. So this is similar, not exactly the same, but it's very similar to the way we would set up a Haas's law equation. And the sum of the individual reactions produce an overall reaction that achieves the desired outcome. Basically, it's because the straight line does not work, so we have to kind of find a workaround. And that's what a coupled reaction is finding a workaround to create a reaction that is usable.